What if our entire civilization, with all its gleaming towers, its global networks, and its relentless hum of activity, is running on borrowed time? We have mastered fire, split the atom, and covered our world in a web of light, yet this very triumph has become our most profound predicament. Every flip of a switch, every journey taken, every byte of data processed is a transaction, a withdrawal from a planetary account that is rapidly approaching zero. A shadow falls over our relentless progress, a whispered anxiety that the engine of our modern world is devouring the very future it was built to secure. We drill deeper, burn hotter, and push our technological limits, all in a desperate search for more power, forever chasing a receding horizon of energy security. We live in the great paradox of the 21st century, a species that can whisper across continents in an instant, yet finds itself tethered to the carbon ghosts of ancient sunlight, trapped in a cycle of consumption that warms our planet and clouds our skies. This insatiable hunger for energy is the great unspoken crisis of our age, a challenge so vast, so fundamental, that it seems to demand nothing short of a miracle. And so we look for that miracle in the familiar places. We look to the sun, a colossal fusion reactor bathing us in power, but its generosity is intermittent, a slave to the rhythm of day and night. We look to the wind, the breath of the planet's heat engine, but it is fickle and untamed. We look to the heart of the atom, unlocking the ferocious power that binds matter together. Yet we are left with a legacy of elemental poisons that will outlive our civilizations by millennia. Each solution we devise, however ingenious, seems to come with its own compromise, its own hidden cost. It feels as though we are trapped in a cosmic cage, limited to the energy we can scrape from the surface of our world or catch from our local star. The scale of our ambition has finally outstripped the scale of our resources, and for the first time in our history, we are forced to confront the possibility of a ceiling to our growth, an end to the story of endless expansion that has defined us. But what if we have been looking in all the wrong places? What if the greatest energy revolution in human history is not about finding a new fuel to burn or a new element to split? What if the ultimate source of power isn't in the brilliant fires of the cosmos or deep within the planetary core, but is hidden in the most overlooked and seemingly desolate place imaginable? What if it lies waiting for us in the absolute total and profound emptiness of space itself? This idea sounds like a fantasy, a violation of the most fundamental laws of our universe. We are taught from childhood that a vacuum is the definition of nothingness. It is the void, the absence of all things, a perfect state of non-existence. In our cosmic imagination, it is the cold, dark, silent canvas upon which the drama of stars and galaxies is painted. To suggest that this nothing could be a source of something, let alone a source of infinite, inexhaustible energy, seems to border on madness. It is a concept so counterintuitive, so contrary to our lived experience, that it feels more like an artifact of science fiction than a subject of serious scientific inquiry. Yet in the strange, unsettling, and often paradoxical world of quantum mechanics, the very foundation of our modern understanding of reality, this madness begins to look like a profound truth. The pioneers of this new physics, peering into the subatomic realm, discovered a universe far more bizarre and alive than anyone had ever dreamed. They found a world where particles could be in multiple places at once, where reality itself seemed to flicker in and out of existence, and where the solid ground of classical physics dissolved into a shimmering sea of probabilities. And in the heart of this quantum revolution, they stumbled upon the most startling revelation of all, that empty space is not empty. It is not a placid, silent void. It is instead a roiling, seething, incandescent cauldron of activity. The quantum vacuum, as it is now called, is a place of unimaginable violence and creation, a foam of space-time where particles of matter and antimatter are constantly erupting into existence, only to annihilate each other in a flash of energy. Moments later, these are not mere mathematical ghosts. They are called virtual particles, and their fleeting existence is a constant ongoing process that permeates every cubic centimeter of the universe. Imagine an ocean perfectly calm on its surface, giving the illusion of stillness. But deep beneath, powerful currents are churning, and countless microscopic lives are being born and dying in every passing second. This is our universe, The quiet of the void is an illusion. Beneath the surface of what we perceive as nothing, there is a hidden fundamental reality, an unseen cosmic hum that represents the baseline energy of space-time itself. This is zero-point energy. It is the energy that remains even when all other forms of energy are removed, the energy inherent in the fabric of reality when it is cooled to absolute zero, the theoretical point where all classical motion ceases. It is the ground state of the cosmos, the ultimate floor of existence. And the amount of energy simmering in this quantum foam is not trivial. According to the calculations of theoretical physics, the numbers are so astronomical they defy comprehension and beggar belief. The energy density of the vacuum is predicted to be so immense that a simple coffee mug filled with nothing but pure empty space should contain enough raw, untapped power to boil all the oceans of the entire world. This is not a small error in calculation. It is a fundamental prediction of our best and most tested theory of reality. We are, it seems quite literally, swimming in an infinite ocean of energy, a wellspring of power so vast that it makes the output of all the stars in the universe combined look like a flickering candle in a hurricane. For decades, this staggering prediction was a source of deep embarrassment for physicists. The discrepancy between the theoretical energy of the vacuum and the observed energy of the cosmos was and remains the single greatest error in the history of science. It was a phantom, a ghost in the machine of quantum mechanics, a number so absurdly large that most scientists simply learned to ignore it, to cancel it out of their equations in a process called renormalization, so they could get on with the business of predicting observable phenomena. But nature has a way of leaving clues, of whispering its deepest secrets to those who are willing to listen. And in 1948, a Dutch physicist named Hendrik Casimir proposed an experiment. He theorized that if this sea of virtual particles was real, then it should be able to exert a real physical force. He imagined two perfectly smooth, uncharged metal plates placed parallel to each other in a perfect vacuum separated by a microscopic gap. Outside the plates, virtual particles of all wavelengths could pop in and out of existence, pushing on the plates from the outside. But inside the tiny gap between them, only particles with a wavelength that fit perfectly into that space could exist. This would create an imbalance. There would be more quantum pressure from the outside pushing in than from the inside pushing out. The plates, he predicted, should be forced together by the pure, unadulterated power of empty space. For years, the force was too small to measure the prediction, too esoteric to test. It remained a theoretical curiosity. But as our technology advanced, as our ability to manipulate the world on the microscopic scale grew more precise, we finally built the experiment. And it worked. The plates moved. The Casimir effect was real. Nothing, it turns out, has weight. The void can push. This single elegant experiment changed everything. It was the first piece of tangible experimental proof that zero-point energy was not just a mathematical fiction. It was a real physical phenomenon. The cosmic hum was no longer just a theory. We had finally built an instrument sensitive enough to hear its faintest whisper. And with that whisper comes the most audacious and tantalizing question in the history of science. If this energy is real, if it can exert a force, can we harness it? Can we build an engine that runs on the fuel of absolute nothingness? Can we drill a well into the fabric of space-time itself and extract the limitless power simmering within? This is the quest we are about to embark upon. It is a journey that will take us from the grandest scales of cosmology to the deepest, most perplexing mysteries of the quantum world. We will meet the brilliant, often eccentric pioneers who dared to take this idea seriously, facing ridicule and skepticism from the scientific establishment. We will explore the labyrinthine physics that governs the vacuum, a world of negative energy, virtual realities, and the very structure of space-time. We will investigate the incredible, almost utopian promise of what harnessing this energy would mean for humanity. It represents a source of power that is infinite, available everywhere in the universe, and produces no pollution, no waste, no carbon dioxide. It is an energy source that would not just power our cities, but could fundamentally reshape our civilization, ending our reliance on finite resources and opening up the solar system, and perhaps even the stars, to human exploration. But we will also confront the formidable, perhaps insurmountable challenges that lie in our path. How do you tap an energy field that is by its very nature uniform everywhere? Extracting energy requires a difference, a gradient, a flow from a high state to a low state. The quantum vacuum, the ground state of the universe, is the lowest possible state of energy. Tapping it might be like trying to drain an ocean that sits at the bottom of the world's deepest trench. It is a technological and theoretical conundrum of the highest order and Everest of physics that some believe we will never be able to climb. The pursuit of zero-point energy is more than just a search for a new power source. It is a journey to the very edge of our understanding of existence. It forces us to ask the most fundamental questions. What is the true nature of empty space? What is the relationship between matter, energy, and the void? And what secrets does the universe still hold hidden in plain sight, waiting for a species curious and bold enough to look at nothing and see the potential for everything? The story of zero-point energy is the ultimate story of scientific exploration, a tale of visionary thinkers, profound mysteries, and a technological dream that, if realized, would represent the single greatest leap forward in human history. It is a dream of infinite power drawn from the silent heart of the cosmos. Our journey into the void begins now, undefined. What if the most profound secret of the cosmos isn't hidden in the fiery heart of a distant quasar or locked away in the cryptic physics of a black hole? What if instead it lies in the most overlooked and seemingly mundane thing imaginable? Nothing at all. We have been taught to think of empty space as a void, a passive stage upon which the drama of the universe unfolds, a silent, cold, and absolute vacuum. But this intuition, born from our everyday experience, is a profound illusion. The story of the 20th century in physics is the story of discovering that the vacuum is not empty. It is a plenum, a seething, turbulent ocean of latent energy, a hidden reservoir of power so vast it defies all conventional scales of imagination. This is the story of how we peered into the abyss and found it staring back not with emptiness but with the promise of infinite potential. It is the genesis of an idea so revolutionary it borders on science fiction, the concept of zero-point energy. Our journey into this paradoxical realm begins not with a bold leap, but with a reluctant whisper, a mathematical fix born of desperation. In the final years of the 19th century, physics stood as a triumphant, seemingly complete edifice of classical thought. Newton's laws governed the heavens. Maxwell's equations had unified electricity and magnetism into the elegant dance of light. Yet one stubborn, dark cloud lingered on the horizon, a problem so vexing it was dubbed the ultraviolet catastrophe. According to the established laws, any hot object should radiate energy across the entire electromagnetic spectrum. But the equations predicted that as the wavelength got shorter, moving into the ultraviolet and beyond the energy emitted should skyrocket to infinity. This was a clear absurdity. An ordinary fireplace should have been blasting us with lethal gamma rays. Reality was stubbornly refusing to obey our most cherished theories. It fell to a German physicist, a man of conservative instinct and deep respect for the classical tradition, to solve this glaring contradiction. His name was Max Planck, and in 1900 he did something he would later call an act of desperation. He proposed that energy was not a smooth, continuous fluid as everyone had assumed. Instead, he suggested it could only be emitted or absorbed in discrete tiny packets, like a currency that only comes in specific denominations. He called these packets quanta. This was not a revolution he wanted to start. It was a mathematical trick, a fudge factor designed to make the equations work. But it did work. By quantizing energy, he perfectly solved the ultraviolet catastrophe and laid the foundation stone for the most successful and bizarre theory in the history of science, quantum mechanics. Yet hidden deep within the elegant simplicity of his own famous equation, E equals hf, was an unintended and far more radical implication. The math suggested that any oscillating system from a pendulum to an electromagnetic field could never be brought to a complete and utter standstill. Even at the theoretical point of absolute zero, the coldest temperature possible where all thermal motion should cease, there remained a residual, irreducible tremor of energy, a final ghostly half-quantum of vibration. This was the first mathematical hint of a fundamental energy flaw to the universe, an energy that exists even in the darkest, coldest, emptiest corner of space. This was the zero-point energy. For decades, this residual energy remained a theoretical ghost, a mathematical footnote that many physicists chose to ignore. It was an artifact of the new quantum rules, but it had no obvious tangible effect on the world. What, after all, is the practical meaning of energy you can't extract or even measure against a background of true nothingness? The universe, it seemed, had a baseline energy level that was simply not zero. But then another German wunderkind, a brash young genius named Werner Heisenberg, would stumble upon a principle so strange, so counterintuitive it would transform this mathematical ghost into a physical necessity. In 1927, Heisenberg unveiled his uncertainty principle, and with it, he shattered our last illusions of a predictable clockwork universe. The principle is a statement of profound cosmic humility. It declares that there are fundamental pairs of properties in nature, like a particle's position and its momentum, which can never be known with perfect simultaneous accuracy. The more precisely you measure one, the less precisely you can possibly know the other. It's not a limitation of our instruments. It is an inherent, baked-in feature of reality itself. You can know exactly where a particle is, but you will have no idea where it is going. Or you can know exactly where it is going, but you will be forever uncertain as to where precisely it is. This cosmic uncertainty is the very engine that drives the zero-point energy. Consider a patch of supposedly empty space. A true void, by definition, would have an electromagnetic field value of exactly zero, and its rate of change would also be exactly zero. It would be perfectly still, perfectly empty, perfectly known. But Heisenberg's principle forbids this. To know both the field's value and its rate of change with perfect certainty would be a fundamental violation of the laws of nature. If the field were truly zero and static, we would know its position and its momentum at the same time. This cannot happen. Therefore, the field can never be truly empty. It must constantly fluctuate, jittering and vibrating around an average value of zero, like a nervous hummingbird that can never land. Space itself is caught in a perpetual quantum tremor, a ceaseless, restless agitation. It is this fundamental, unavoidable quantum jitter that constitutes the zero-point field. Planck's mathematical ghost had just been given a physical heartbeat, a pulse driven by the very uncertainty that underpins all of existence. The vacuum was no longer a silent stage. It was a restless, dynamic entity buzzing with potential. These fluctuations are not just abstract waves in a field. They have a physical character, one that is almost impossible to reconcile with our sense of reality. They manifest as a ghostly blizzard of what physicists call virtual particles. In the quantum vacuum, for infinitesimally brief moments, pairs of particles and their antimatter counterparts can spontaneously burst into existence, borrowing their energy from the vacuum itself. A virtual electron and a virtual positron, for example, might pop into being, exist for a fleeting fraction of a second, and then collide and annihilate one another, repaying their energy debt to the void. This process is happening everywhere, all the time, in every cubic centimeter of space you inhabit. Right now, your body is being traversed by an incomprehensible number of these phantom particles. They are a ghost tide washing through the entire universe. They are not real in the way a stable proton or electron is. They exist on a loan from Heisenberg's uncertainty, a form of cosmic embezzlement where energy can be borrowed from the future, so long as it's paid back almost instantly. The more energy borrowed, the shorter the loan term. This creates a roiling, bubbling, chaotic sea of transient existence, a phenomenon often called quantum foam. It is a seething soup of possibility, a constant symphony of creation and annihilation that plays out on the smallest possible scales of space and time. To a classical physicist, this sounds like pure fantasy, a descent into mysticism, a sea of ghostly particles borrowing energy from nothing, flickering in and out of being. It seems to violate one of the most sacred tenets of physics, the conservation of energy. But in the strange world of quantum mechanics, this law can be briefly suspended, allowing for these energetic fluctuations to occur. And while each individual virtual particle is an ephemeral phantom, their collective presence is not. Their combined, ceaseless activity imbues the vacuum with an astonishing property, an enormous underlying energy density. Early calculations for this energy density produced numbers that were staggeringly astronomically large. If you were to take all the energy locked away in the virtual particles within a single light bulb, the resulting figure would be, according to the theory, more than enough energy to boil all the oceans on Earth. This was and remains a monumental puzzle. The theory predicted an ocean of unimaginable power, yet we sail through it every day without noticing a ripple. Why doesn't this immense energy collapse the universe? Why don't we see its effects everywhere? For many years, this was the state of affairs, a beautiful, strange, and deeply unsettling theory with a wild prediction of a vast energy, but with no way to prove it was truly there. The zero-point field was a ghost story told by theorists a whisper in the equations. That is, until 1948, when a Dutch physicist provided the first piece of hard, tangible evidence that the ghost was real. His name was Hendrik Casimir, and like Max Planck, he was not looking for a revolution. He was a practical scientist working at Philips Research Laboratories in the Netherlands, tasked with a seemingly mundane industrial problem. He was investigating the properties of colloidal fluids, which are suspensions of fine particles in a liquid like milk. He needed to understand the subtle, long-range attractive forces between molecules known as van der Waals forces. As he and his colleague Dirk Polder delved into the quantum mechanical calculations, they found something deeply puzzling. Their math predicted that at large distances, the force between two neutral atoms should behave differently than expected. Seeking an answer, Casimir visited the legendary physicist Niels Bohr in Copenhagen. During a conversation, Bohr mumbled something almost as an aside. It must have something to do with the zero-point fluctuations. The idea struck Casimir like lightning. He rushed back to his calculations, reframing the problem not as a force between two molecules, but as a change in the zero-point energy of the vacuum times caused by times the presence of the molecules. This new approach worked perfectly. Emboldened, he simplified the problem into an elegant and audacious thought experiment. Imagine taking two perfectly reflective, uncharged metal plates and placing them parallel to each other in a perfect vacuum just a few microns apart. Classically, nothing should happen. There is no charge, no gravity of any significance, no air pressure. The plates should remain motionless, suspended in absolute emptiness. But Casimir realized the vacuum wasn't empty. It was a roiling sea of virtual particles, an ocean of quantum waves of every possible wavelength. He understood that these waves, these fluctuations, would exert a kind of pressure. Outside the two plates, the quantum foam could fluctuate wildly with virtual photons of all wavelengths popping in and out of existence. But the space-times between times, the plates acts as a resonant cavity. Only virtual photons whose wavelengths fit neatly into that tiny gap are permitted to exist there. Longer wavelengths are excluded. It's like comparing the waves on the open ocean to the water in a calm, narrow harbour. The turbulent, high-energy waves of the open sea are suppressed within the confines of the harbour walls. In the same way, there are more quantum waves, more virtual particles in the vacuum outside the plates than there are in the sheltered space between them. This imbalance creates a net pressure. The more energetic vacuum outside pushes the plates together. It is a force conjured from absolutely nothing. A whisper from the void made manifest. This prediction, which became known as the Casimir effect, was one of the most bizarre and profound in all of modern physics. It suggested that one could create a measurable physical force simply by manipulating the geometry of empty space. For nearly 50 years, the effect was too small to be measured, with the technology of the day remaining a tantalizing theoretical prediction. But in 1996, Stephen Lamoureux at the University of Washington finally performed the delicate experiment using a torsion pendulum to measure the faint but undeniable attraction between a plate and a sphere. The results matched Casimir's predictions perfectly. The experiment was later repeated, with even greater precision, by other teams confirming it beyond any doubt. The ghost had finally materialized. The Casimir effect was the first concrete experimental proof that the energy of the vacuum is real. It is not a mathematical fiction, it is a physical phenomenon that can push and pull on real-world objects. The quantum foam is not just a theorist's dream. It is a tangible feature of our universe, an invisible ocean whose waves we can now feel lapping against the shores of our technology. We had spent a century peeling back the layers of reality, moving from the classical world of certainty into the strange probabilistic landscape of the quantum. We began with a German physicist trying to fix a broken equation and ended with the definitive proof that empty space itself is a powerhouse. We have uncovered a fundamental energy field that permeates every fiber of the cosmos, from the space between your atoms to the vast, cold darkness between the galaxies. It is the baseline reality, the energetic bedrock upon which everything else is built. The mystery that Planck and Heisenberg stumbled upon has been transformed into an experimental fact. The ocean of zero-point energy is real. Its existence is no longer in question. And this revelation leaves us standing at the edge of a precipice, staring into an abyss of possibility. We have proven this unseen reservoir of power is there, woven into the very fabric of space-time. But knowing an ocean exists and knowing how to sail it are two very different things. How do we build a ship? How do we dip our bucket into this infinite ghostly sea and draw up the power that lies within? And so with this revelation, the very concept of nothing is erased from the cosmic dictionary. Empty space is a lie. What we had perceived as a silent, placid void is in fact a turbulent ocean of pure potential, a roiling sea of virtual particles flashing in and out of existence faster than our senses could ever register. But to leave the story there with the mere existence of this energy is like discovering fire and only remarking on its warmth. The truly staggering part of the journey begins now, when we dare to ask the next question: what are the consequences of living inside this invisible storm? What does this phantom energy actually do times? The answer we would find would not just challenge our understanding of technology or power, it would threaten to shatter the twin pillars of modern physics themselves. Our first clue to its immense power came not from an engineering lab, but from the blackboards of cosmologists grappling with the ultimate fate of the universe. For over a century, we've known the universe is expanding, but in the late 1992, observations of distant supernovae revealed a terrifying truth: that expansion is accelerating. Something is pushing the cosmos apart, a mysterious anti-gravitational force embedded in the very fabric of space-time. Physicists call it dark energy, and its simplest theoretical explanation is something Einstein himself once imagined and later discarded as his biggest blunder: the cosmological constant. It is a fundamental energy density inherent to the vacuum of space itself. Suddenly, his blunder looked like prophecy, and in the shimmering quantum foam of zero-point energy, scientists saw a perfect candidate. Here, finally, was an energy of the vacuum, a universal intrinsic pressure that could be driving the cosmos to its eventual lonely end. The pieces seemed to fit perfectly. Quantum mechanics, the science of the very small, provided a source for the mysterious force observed by cosmology, the science of the very large. It was a moment that should have been a grand unification, a triumphant symphony of scientific discovery. Instead, it became a nightmare. It became the single greatest failure of a physical theory in the history of science. When physicists took the equations of quantum field theory and attempted to calculate the theoretical energy density of the vacuum based on zero-point energy, they arrived at a number. It was a definite, unambiguous prediction. It was also a number so catastrophically comically wrong that it has haunted physics for decades. The energy density predicted by our best theory of the quantum world is not just a little off from the observed value of the cosmological constant. It's not off by a factor of 10 or 1,000 or even a trillion. The theoretical value is 120 orders of magnitude larger than what we observe. That's a 1 followed by 120 zeros. To put that into perspective for you is almost impossible. It is a number larger than every atom in the known universe. If the observed energy of the cosmos, the gentle cosmic push, is the soft whisper of a single falling leaf, the energy predicted by our theories is a sound loud enough to vaporize galaxies. It's a cosmic accounting error of such monumental proportions that it has a name: the vacuum catastrophe. It is a fundamental crack running through the heart of physics. If the zero-point energy field were truly that powerful, galaxies would have never formed. Stars would have been blasted apart before they could ignite. The universe as we know it would be an incandescent, ever-expanding fireball, ripped asunder by the sheer violence of its own empty space in the first femtosecond of its existence. And yet here we are. We live in a calm, structured, and only gently accelerating cosmos. This implies one of two possibilities. Either our understanding of quantum mechanics is profoundly incomplete, or some other completely unknown physical law is at play, cancelling out nearly all of this immense energy with an almost perfect, incomprehensible precision. It's like witnessing two titans engaged in an epic struggle, each unleashing enough force to shatter worlds, yet their powers are so perfectly matched that the result is a near-perfect stillness, leaving behind only the faintest tremor. We are living in that tremor, oblivious to the war being waged in every cubic centimetre of space around us. The vacuum catastrophe is more than a puzzle. It's a profound statement about our own ignorance. The most successful theories ever conceived by humanity, general relativity and quantum mechanics, give us completely irreconcilable answers to the same question. They cannot both be right as they currently stand. The omnipresent sea of ZPE, therefore, is not just a potential power source. It is the universe's greatest unsolved paradox, a ghostly sentinel standing guard at the border of our knowledge. Confronting this paradox forces us to face a far more practical problem. How do you even begin to measure, let alone harness, an energy that is everywhere at once? It is the ultimate background, the canvas upon which reality is painted. Interacting with it directly is like trying to feel the wind while flying at the same speed as the wind itself. You can't scoop it up in a bucket because the bucket is already full of it. You can't isolate it because there is nowhere to isolate it times from asterisk. It is the baseline, the absolute zero of the cosmic energy scale from which everything else is measured. This is why for decades many physicists treated it as a mere mathematical artifact, a quirky infinity that could be conveniently renormalized or subtracted away from their equations to get answers that matched experiments. It was a ghost in the machine of physics, a constant you could cancel out without consequence. Or so they thought, because the ghost, it turns out, has a shadow, and where there is a shadow there must be a source. In 1948, the Dutch physicist Hendrik Casimir conceived of an experiment, a brilliant and elegant way to prove that the phantom sea was real. He reasoned that while you cannot see the ocean itself, you might be able to detect its waves. His idea was deceptively simple. Imagine two perfectly smooth, uncharged metal plates placed parallel to each other in a perfect vacuum, separated by only a few micrometers. Outside the plates, the quantum vacuum can produce virtual particles, quantum fluctuations of every possible wavelength, an infinite sea of possibilities. But times between times the plates, it's a different story. The tiny gap acts as a resonant cavity. Only virtual particles with wavelengths that fit neatly into that gap can pop into existence. Longer wavelengths are excluded. This means there are more quantum waves, more virtual particles pushing on the times outside times of the plates than there are on the times inside asterisk. The result Casimir predicted should be a net force, an inexorable pressure born from the raw vacuum of space-time pushing the two plates together. It would be a force from nothing, a physical manifestation of the zero-point energy field. For nearly 50 years, Casimir's prediction remained a theoretical curiosity, a clever thought experiment beyond our technical ability to verify. The force was predicted to be incredibly tiny, easily swamped by thermal vibrations or stray electrostatic charges. But in 1996, at the Los Alamos National Laboratory, physicist Steve Lamoureux finally conducted the experiment with enough precision. Using a delicate torsion pendulum, a device of exquisite sensitivity, he brought the plates together in a near-perfect vacuum. And he saw it. A force. A tiny, persistent, undeniable force, precisely matching the predictions made by Casimir half a century earlier. It was there. The ghost was real. The Casimir effect was the first tangible proof that the zero-point field was not just a mathematical trick. It was a physical reality, a universal ocean, that could exert real, measurable pressure on our world. It was the first hint that this background energy was not untouchable. That perhaps, just perhaps, if you could engineer the boundaries of the vacuum itself, you could make its immense power work for you. The discovery opened a floodgate, transforming ZPE from a cosmological problem into an engineering frontier. If the vacuum could push, could it also be made to pull? Could we, instead of being tossed about by this cosmic ocean, learn to build a sail? This question led directly to one of the most tantalizing and speculative ideas in all of physics: faster than light travel. The laws of relativity are strict. They build a cosmic speed limit, the speed of light, and forbid any object with mass from ever reaching it. Traveling to the nearest star, Proxima Centauri, would still take a conventional rocket tens of thousands of years. The universe, for all its grandeur, would remain an unreachable shore. But what if you didn't have to travel times through time's space? What if you could make space itself travel for you? In 1994, theoretical physicist Miguel Alcubierre proposed a radical solution, one that doesn't break Einstein's laws, but rather exploits a loophole in them. His concept, now known as the Alcubierre drive or warp drive, envisions a spacecraft enclosed in a bubble of space-time. This bubble would be propelled by contracting space-time in front of it and expanding space-time behind it. The ship inside the bubble wouldn't actually be moving at all relative to its local environment. It would be a passenger carried along on a moving wave of space-time itself. From the perspective of an outside observer, the ship could appear to travel at many times the speed of light, crossing interstellar distances in mere weeks or days, all without violating the laws of relativity. It was a breathtaking vision, a mathematical blueprint for humanity's future among the stars. But it came with one enormous, seemingly impossible catch. To create this effect, to warp and bend space-time in such a precise way, you would need something extraordinary. You would need a source of what physicists call negative energy density, or exotic matter. You would need to create a region of space that has less energy than the surrounding vacuum. For a long time, this was considered a deal-breaker, a fantasy ingredient from science fiction. But then, scientists looked back at the Casimir effect. The very region between those two plates, the space where certain quantum fluctuations are excluded, is a region with a lower energy density than the normal vacuum outside. It is times a region of negative energy density. Suddenly, the impossible ingredient for a warp drive had a potential source. The zero-point field itself, the very energy that permeates all of existence, held both the problem and the potential solution. The Casimir effect, while far too weak to power a starship, provided a proof of concept. It showed that manipulating the quantum vacuum to produce the exotic effects needed for a warp drive was not in principle forbidden by the laws of physics. The challenge was no longer one of possibility but of scale. Could we engineer materials and electromagnetic fields so advanced that they could amplify this tiny quantum effect, sculpting the vacuum on a macroscopic level? Could we build a machine that could create a bubble of negative energy large enough to hold a spacecraft? The idea that our ultimate destiny in the cosmos might be unlocked not by more powerful rockets, but by understanding the subtle energy of absolute nothingness was a revolution in thought. This tantalizing potential has for decades attracted visionaries and mavericks to the fringes of mainstream science. When an idea promises infinite energy and interstellar travel, it inevitably becomes a powerful magnet for those willing to dream beyond the confines of accepted theory. The history of ZPE research is therefore a tangled narrative, a complex story woven with threads of brilliant insight, controversial claims, and outright speculation. It is a landscape where distinguishing the frontier of science from the realm of fiction becomes a daunting task. Figures like physicist Harold Puthoff, for example, have long proposed that zero-point energy is not just a background sea, but is intimately involved in the most fundamental aspects of our reality. He has advanced theories suggesting that phenomena like inertia and gravity are not inherent properties of matter, but are in fact interactions between matter and the zero-point field. In this view, an object's resistance to acceleration, its inertia, is the drag it experiences as it plows through this energetic quantum sea. Gravity likewise could be reinterpreted as a subtle pressure from ZPE, a kind of cosmic shadow cast by massive objects. These are deeply provocative ideas. If true, they would rewrite physics from the ground up. They suggest that by learning to modulate the ZPE field around an object, we could theoretically reduce its mass, or even create artificial gravitational fields, opening the door to propulsion systems that would make our current rockets look like stone tools. Such concepts have led to a shadow world of research, often conducted outside of major universities and funded by private investors captivated by the promise of revolutionary technology. Inventors have filed patents for devices claimed to extract usable energy from the vacuum, often citing misunderstood principles of quantum mechanics. These claims are almost universally met with extreme skepticism from the broader scientific community, and for good reason. The laws of thermodynamics, particularly the conservation of energy, are the bedrock of our physical understanding. The idea of a free energy device that taps an infinite reservoir seems to violate these sacred principles. Most physicists argue that ZPE is the lowest possible energy state of the universe, the ground state. By definition, you cannot extract energy from the ground state any more than you can make water fall from the bottom of a waterfall. Yet the proponents argue that thermodynamics applies to closed systems, and a device interacting with the entire quantum vacuum of the universe is by no means a closed system. They point to the Casimir effect as irrefutable proof that energy can be manifested from the vacuum, even if only in the form of a force. The debate rages on, often creating a deep chasm between theoretical possibility and experimental reality. The challenge for us and for the scientists on this quest is to maintain a delicate balance. We must hold on to the rigorous skepticism that is the hallmark of good science, demanding extraordinary evidence for extraordinary claims. But we must also preserve the open-minded curiosity that allows us to explore the edges of what is possible, to ask the what-if questions that so often precede a great leap forward. The story of zero-point energy is a lesson in that balance. It is a field littered with dead ends and false prophets, but it is also a field that touches upon the most profound and unanswered questions in all of physics. To dismiss it entirely is to ignore the vacuum catastrophe and the undeniable reality of the Casimir effect. To embrace every claim uncritically is to abandon the scientific method. The true path forward lies somewhere in the difficult, uncertain middle ground. The theoretical key forged in the mathematics of quantum field theory and cosmology is now in our hands. It tells us that a power of unimaginable magnitude lies dormant in every breath of space you take, but the lock is the universe itself, a mechanism of such complexity and subtlety that we are only just beginning to understand its design. The question that defines our time is no longer is the energy there, but can we ever hope to turn the key? The answer will not be found in old theories or speculative patents. It is being sought right now in quiet laboratories with new tools and a new generation of scientists, the quantum locksmiths of the 21st century. They are the ones wrestling with the ghost in the machine, attempting to transform the most profound paradox in science into humanity's greatest source of power. And so, with the math seemingly unassailable and the evidence of the Casimir effect, a tantalizing microscopic proof, the question changed. It was no longer times if times this energy existed, but a far more dangerous, far more seductive question. Could we touch it? Could we reach into the nothingness and draw forth something? The ghost in the quantum machine was about to be invited into the world of gears and wires. This was the moment the dream of the theorists became the obsession of the engineers, a pivot point where the elegant abstraction of the vacuum began its messy, chaotic, and exhilarating journey toward concrete reality. It was a journey that would split into two paths, one bathed in the cold light of scientific rigor, the other illuminated by the flickering torchlight of fervent belief. The first steps down that legitimate path were taken by minds uniquely positioned between established physics and speculative fiction. One of the most brilliant was Robert Forward, a physicist at the prestigious Hughes Research Labs. Forward was a man who lived with one foot in the world of peer-reviewed papers and the other in the limitless expanse of interstellar travel and alien civilizations, for he was also a celebrated science fiction author. This dual vision allowed him to see the zero-point field not just as a feature of quantum mechanics, but as a potential engineering resource. In the 1,980 seconds, he began to publish papers that were for the time breathtakingly audacious. He wasn't just talking about the ZPE, he was sketching blueprints for how to use it. He imagined devices that could, in theory, manipulate the very fabric of the vacuum. One of his most famous thought experiments involved what you might call a vacuum battery. Picture a microscopic accordion, its plates made of a flexible conductor. According to the Casimir effect, when these plates are brought incredibly close, the vacuum energy between them is lower than the energy outside. This creates a net force pushing them together. Forward reasoned that if you could use a tiny amount of external energy to pull these plates apart, you would be working against that vacuum pressure. Then, if you let the plates collapse back together on their own, the vacuum itself would do the work, releasing a burst of energy. If you could somehow extract more energy from the collapse than you spent pulling them apart, you would have a net energy gain drawn directly from the quantum foam. It was a concept of sublime elegance and nightmarish technical difficulty. The scales were subatomic, the forces infinitesimal, and the materials required to build such a device were beyond anything available. Yet the proposal was grounded in established physics. It wasn't magic, it was engineering, albeit an engineering for a distant future. Forward's work was a clarion call. He had taken the ethereal concept of zero-point energy and placed it for the first time on an engineer's drafting table. He treated the vacuum not as a passive void, but as an active mechanical medium, a wellspring that could perhaps be tapped with a sufficiently clever pump. His papers became foundational texts for a small but growing community of physicists who dared to ask, what if? Around the same time, another formidable intellect, Harold Hal Puthoff, began publishing a series of equally provocative papers. Working first at SRI International and later at the Institute for Advanced Studies at Austin, Puthoff took an even more radical approach. He wasn't just trying to extract energy from the vacuum, he was proposing that some of the most fundamental forces of our reality times were time's effects of the vacuum. He suggested that gravity itself might not be a fundamental force, not the elegant curvature of space-time that Einstein described, but an emergent phenomenon. In his model, gravity was a residual force, an after-effect created by the interaction of matter with the roiling sea of zero-point fluctuations. Imagine an object placed in this energetic ocean. The quantum fields push on it from all sides. But when you bring two objects near each other, they cast a shadow. Each object shields the other from some of the fluctuations coming from the far side. This creates an imbalance, a net pressure pushing the two objects together. That pressure, Puthoff argued, is what we perceive as gravity. It was a stunning reinterpretation of one of cosmology's deepest mysteries, an attempt to unite the quantum world with the gravitational world through the medium of the vacuum. He went even further. Puthoff proposed that inertia, the resistance of an object to acceleration, was also a product of the ZPE field. When you try to push an object, you are not fighting some innate property of the object itself, but rather you are forcing it to move against the backdrop of this universal energy field. The object interacts with the zero-point fluctuations, creating a kind of electromagnetic drag, a resistance that we experience as inertia. In this view, every object in the universe, from a speck of dust to a galaxy, is constantly interacting with the vacuum, its very existence and motion defined by this unseen ocean. If this were true, the implications were staggering. If you could learn to modify the local zero-point field around a spaceship, you could theoretically reduce its inertia, allowing for accelerations impossible to achieve by any other means. You could engineer gravity itself. These were not idle speculations. They were detailed mathematical theories published in respected journals like Times Physical Review**. Forward and Puthoff were throwing down a gauntlet. They were telling the scientific community that the vacuum was not empty, not quiet, and not just a subject for esoteric thought experiments. It was a player. It was perhaps the time's central player in the cosmic drama, and the time had come to understand its rules and just maybe learn to bend them. Their work lit a fuse, creating a legitimate, albeit small field of inquiry into the engineering potential of the quantum vacuum. But that same fuse also lit a fire in a very different world, a world far from the cautious peer-reviewed process of institutional science. It was here the path forked, For every physicist like Forward or Puthoff meticulously checking their equations, there were now a dozen inventors in garages and basements, inspired by the same grand promise, but unburdened by the same scientific rigor. The siren song of free energy had been sung for centuries, a perennial anthem for inventors hoping to defy the laws of thermodynamics. But now, with the advent of zero-point energy, this old song had a new, powerful, and scientifically adjacent lyric. The term ZPE became a kind of magic word, a veneer of quantum legitimacy that could be applied to any number of exotic devices. This was the birth of the modern free energy movement, a cultural phenomenon that would grow to shadow and often poison the legitimate scientific search. Suddenly, claims began to bubble up from the fringe. Self-proclaimed geniuses announced they had built machines that could power a house from a small box fueled by the vacuum of space. They spoke of over-unity devices, machines that produced more energy than they consumed, seemingly violating the most sacred laws of physics. These inventors were often charismatic figures, casting themselves as lone visionaries, fighting a conspiracy of silence from big oil companies and governments who wanted to keep humanity chained to fossil fuels. They held dramatic press conferences, showcased whirring, blinking contraptions, and spoke of a new dawn for humanity. The promise was irresistible, limitless, non-polluting power for everyone, an end to poverty, an end to war over resources. It was a technological utopia, powered by the very emptiness of space. The devices themselves were often a bewildering assortment of magnets, coils, and crystals, bearing names like the magnetic resonance amplifier or the quantum energy generator. The explanations were a thick stew of legitimate scientific terms, misused and misunderstood, mixed with esoteric and mystical concepts. They would talk of tapping the ether, tuning to the resonant frequency of the vacuum, and creating a portal to the zero-point field. For the public, and even for journalists without a deep physics background, it was nearly impossible to separate the plausible from the preposterous. The inventors performed demonstrations that seemed convincing. A bank of light bulbs would be lit, seemingly powered by a small self-contained box with no obvious power source. But under the cold, unforgiving eye of scientific scrutiny, these claims invariably dissolved. The bedrock of physics, the law of conservation of energy, states that energy cannot be created or destroyed, only changed from one form to another. A machine that produces more energy than it consumes is as physically impossible as a machine that pulls itself up by its own bootstraps. When independent investigators were finally allowed to examine these devices, if they were allowed at all, the trick was always revealed. A hidden battery, a cleverly concealed wire running up a table leg, a miscalibrated meter. Sometimes the deception was deliberate fraud. More often, it was a case of tragic self-delusion, an inventor so blinded by their own hope that they measured their inputs and outputs, incorrectly fooling themselves before they fooled anyone else. The pattern became depressingly familiar. A grand announcement would be made, followed by a call for investment. When pressed for independent verification by a reputable lab, the inventor would refuse, claiming their technology could be stolen. They would speak of persecution, of threats from shadowy forces. They would argue that mainstream science was simply too closed-minded to understand their revolutionary principles. And then, inevitably, the inventor and their miraculous device would fade into obscurity, leaving behind a trail of disappointed investors and a public more confused than ever. This fusion of genuine utopian yearning, scientific illiteracy, and outright hucksterism created a toxic environment. The collision between the legitimate scientific pursuit and this burgeoning fringe movement was inevitable, and its consequences were devastating for the real science. The term zero-point energy became tainted by association. In the halls of academia and at major funding agencies, it became a career killer, a red flag that marked a researcher as a crank. Scientists who might have been interested in exploring the speculative but legitimate ideas of figures like Puthoff and Forward now shied away, fearing for their reputations. To even mention ZPE in a grant proposal was to invite ridicule and rejection. The serious, disciplined inquiry into the nature of the vacuum was driven deeper underground, starved of funding and mainstream attention. The fringe movement, in its noisy and theatrical quest for a miracle, had ironically made the slow, difficult search for a genuine breakthrough nearly impossible. It had muddied the waters so thoroughly that it became difficult to see the real science through the murk of pseudoscience. A profound schism had occurred. On one side, you had a handful of dedicated, credentialed physicists working in near isolation, publishing dense theoretical papers in specialized journals, their work proceeding at the glacial pace of true science. On the other, you had a loud, vibrant, and sprawling subculture of believers, conventions and YouTube channels, all convinced that the energy revolution was here, perpetually, just one breakthrough away, if only the conspiracy could be overcome. Yet even in this chilled climate, the legitimate scientific spark refused to be extinguished completely. Behind the scenes, the theoretical work continued to evolve, growing more sophisticated. Physicists began to think about the problem in new ways, moving beyond the simple static Casimir effect. They began to explore the dynamic Casimir effect. The idea was that if you could wiggle a mirror back and forth at incredible speeds, a significant fraction of the speed of light, its rapid acceleration through the vacuum could convert some of those virtual photons into real detectable particles of light. You would, in essence, be shaking light out of the empty darkness. The energy required to move the mirror would be immense, far more than you'd get back, but it was another theoretical proof of principle. The vacuum was not immutable. It could be acted upon. It could be made to yield its secrets and its energy. More complex proposals emerged, ideas about creating specially shaped cavities whose resonant frequencies could be rapidly altered with superconducting circuits. The goal was to manipulate the boundary conditions of the vacuum faster than the field could settle, creating a momentary imbalance that could be exploited to bleed off a tiny amount of energy. Think of it like a child on a swing. By pumping their legs at just the right moment in the arc, changing the system's parameters at the right frequency, they add energy to the swing's motion. Could we pump the vacuum in a similar way, not with legs, but with fluctuating electromagnetic fields and exotic metamaterials to build up and extract energy? The engineering challenges remained astronomical, verging on impossible, but the theoretical pathways were being mapped. Alternative frameworks like stochastic electrodynamics continued to be explored. This theory treats the zero-point field not as a quantum abstraction, but as a real classical fluctuating electromagnetic field that pervades all of space. It offered another mathematical language to describe the same phenomena, one that some physicists hoped might offer a more intuitive handle for engineering concepts. The quest was still alive, surviving in the quiet corners of theoretical physics departments and in the patient long-term visions of a few government and private labs. They knew the journey was not about a miraculous black box, but about a painstaking generational effort to understand the most fundamental and powerful substance in the cosmos. The landscape at the end of this tumultuous period was therefore one of deep and troubling contradiction. The theoretical foundation for zero-point energy was stronger than ever, its existence confirmed by experiment. The tantalizing possibility of it being linked to gravity, inertia, and the very structure of the cosmos was a legitimate, if speculative, frontier of physics. Yet its public face had become a mask of pseudoscience, its name a punchline in university common rooms. The grand dream of powering our world from the void had survived its initial theoretical birth, only to find itself navigating a treacherous landscape of charlatans, true believers, and the profound scientific scorn they had engendered. The central challenge had become twofold. Not only did we need to solve the immense technical hurdles to tap this energy, but we first had to rescue the dream itself from the dreamers who had nearly loved it to death. The question now hanging in the air was whether modern science, with all its new tools and technologies, could finally succeed where so many others had failed and build a bridge across the chasm that now separated the promise of the vacuum from the reality of our world. But for every dazzling summit of human ambition, there is a treacherous descent into the valley of reality. The dream, as we have seen, is intoxicating, a vision of silent, inexhaustible power drawn from the very fabric of the cosmos, a promise whispered by the universe itself, suggesting that the frantic scramble for finite resources might one day be a forgotten relic of a primitive past. It's a tantalizing picture, a future sculpted from light and limitless potential. Yet, as we turn from the shimmering peaks of theory to the unforgiving terrain of practice, the whispers fade, replaced by the roar of fundamental laws and the deafening silence of failed experiments. This is the downward path, the sobering journey into the labyrinthine reasons why the greatest treasure chest in the universe remains locked, its key seemingly forged from impossible physics. The first wall we hit is not one of engineering, but of perception. A brutal mismatch of scale that defies our macroscopic intuition. You are standing in what appears to be an empty room, yet you know the air around you seethes with the kinetic energy of countless molecules, a hidden thermal reservoir of immense power. Could you run a generator with it? Not unless a corner of the room was inexplicably freezing cold while another was blazing hot. Without a gradient, without a difference, that vast energy is just a uniform, unusable hum. The quantum vacuum presents us with precisely this dilemma, but on a scale that is almost comically extreme. The energy is there, an ocean of it, but it is an ocean at perfect equilibrium with itself. It has no tides, no currents, no waves we can easily harness. To try and extract its power is like trying to sail a ship by pushing on the perfectly still water you are already floating in. Imagine shrinking down smaller than a microbe, smaller than a cell, beyond the very atoms that make up your world. You arrive in a place of pure chaos, the so-called quantum foam. It is not empty. It is a roiling, violent seascape of potential. Here, for slivers of time so brief they mock our understanding of an instant, particles of matter and antimatter flash into existence, borrowing their being from the vacuum itself. They meet, they annihilate, and they vanish, repaying their debt to reality in a constant frenetic cycle of creation and destruction. This is the source of zero-point energy, this endless effervescent storm of virtual particles, and the sheer density of this energy, as we've calculated, is staggering, astronomical. But how do you possibly tap a hurricane that is smaller than a proton and lasts for less than a zeptosecond? It's like trying to quench your thirst from a mist so fine the droplets exist for a shorter time than it takes light to cross a single atom. The energy is not organized. It possesses no direction. It is the ultimate expression of random isotropic noise, pushing and pulling in all directions at once, with perfect, maddening symmetry. Any device we place in this foam is battered from every side equally. There is no net force, no discernible flow, no cosmic wind to turn a celestial turbine. To extract useful work, you need coherence, you need order, you need a flow from a high state to a low state. But the vacuum is the baseline. It is the ground state of all reality, the lowest rung on the cosmic energy ladder. Asking it to give up its energy is like digging a hole in the bottom of a hole. You're asking the universe to fall below its own floor. This isn't just a technical challenge that a clever inventor might one day solve with a new kind of coil or crystal. It's a conceptual paradox that strikes at the very heart of what energy times is, times and how it behaves. The universe, it seems, has built its foundation on an energy source that is simultaneously infinite and infinitely inaccessible. And this is where we meet the great unyielding gatekeeper of physics, the second law of thermodynamics. It is not merely a suggestion or a guideline. It is the most robust and battle-tested principle in all of science, a fundamental rule about the direction of time and the flow of energy. The second law is the universe's accountant, and it is merciless. It dictates that useful energy or low entropy will always flow toward a state of uselessness or high entropy. A hot star radiates its focused, ordered energy into the cold, disordered void. A battery discharges its chemical potential into heat and light. A living being consumes organized matter to maintain its structure against the relentless tide of decay. In every single interaction we have ever observed, the net entropy of the universe increases. Order always dissolves into chaos. This is the arrow of time. Now consider the quantum vacuum in this context. It is at its own scale a system in a state of maximum entropy. It is a perfectly uniform thermal bath, a chaotic fizz of energy with no hot spots or cold spots, no exploitable differences. To pull ordered, useful energy out of this chaotic, disordered state would be like expecting the scattered molecules of smoke from an extinguished candle to spontaneously reassemble themselves back into a perfect, unlit wick. It would be a violation of the second law on a scale so profound it would invalidate nearly all of modern physics. It would mean that time itself could in principle run backwards. The universe does not give up its treasures for free. it always demands a tax, and that tax is paid in the currency of increasing disorder. A machine that could draw limitless energy from the vacuum would be an engine of perfect order, a so-called perpetual motion machine of the second kind, a device that could create oases of low entropy without paying the requisite entropic price elsewhere. And for 2 centuries, physics has taught us that such a machine is an absolute impossibility. But what about the one tantalizing exception we have? The single piece of experimental proof that we can in fact touch this energy, the Casimir effect. As we've explored by bringing 2 perfectly smooth, uncharged plates infinitesimally close together in a vacuum, a force arises from nothing pushing them together. This force is real. It is the vacuum energy in action, a measurable whisper from the quantum foam. For a fleeting moment, it seems we have our loophole. The space between the plates restricts which virtual particles can pop into existence, creating a region of slightly lower energy density between them compared to the space outside. This pressure difference, this tiny energy gradient, generates the force. So couldn't we build a microscopic engine of moving plates? Harvesting this pressure to do work, here the universe reveals its cruelest joke. Yes, you can create this sliver of a lower energy state. You can, for a moment, build a basement beneath the universe's floor, but the cost of entry is astronomical. The energy you must expend to create the apparatus to polish the plates to atomic smoothness, to shield them from all thermal and electrical interference, and most critically, to push them together against the very force you are trying to harness, and then pull them apart again to reset the cycle is orders of magnitude greater than the minuscule puff of energy you could ever hope to extract. It's like spending $1 million to build a machine that can squeeze a single penny out of thin air. You haven't created free energy, you have simply performed an incredibly inefficient energy conversion. You've taken a large amount of high-quality electrical and mechanical energy and transformed it into a tiny amount of mechanical energy and a great deal of waste heat, all while interacting with the vacuum in a scientifically fascinating but pragmatically useless way. The thermodynamic gatekeeper lets you peek at the treasure, but slams the door shut the moment you try to walk away with it. This brutal gap between a tantalizing physical effect and a workable technology has created a vast and sorrowful landscape of misguided dreams. It is a wilderness filled with the ghosts of failed inventions, a graveyard of hope where garage tinkerers and amateur physicists have dashed themselves against the unbreakable walls of physical law. For decades, the field of ZPE extraction has been haunted by a parade of devices often presented with breathless fanfare that promise to deliver on the dream. They come with exotic names, complex diagrams of coils and magnets, and fervent testimonials. Yet one by one they fall. They fail to be replicated by independent labs. They are revealed to be drawing power from hidden sources, or they simply quietly stop working. The story is almost always the same. An inventor, often brilliant but working in isolation, builds a complex electromagnetic device. They switch it on, and their instruments register an anomaly, more power coming out than they seem to be putting in. They believe they have finally done it, that they have opened the valve to the infinite reservoir. But what they have likely found is not a new law of physics, but a subtle error in measurement. The world of electronics is notoriously noisy. Stray radio frequencies from a nearby broadcast tower, grounding loops in the lab's wiring, resonant effects in the circuitry that allow it to draw power from the grid with unusual efficiency, even simple chemical reactions in the devices. Components can all create the illusion of overunity, power. The desire to believe is so powerful that it creates a kind of confirmation bias, where every flicker on an oscilloscope is interpreted as a sign of success, and every mundane explanation is dismissed as the skepticism of a closed-minded establishment. We see this pattern repeat with sonoluminescence, the strange phenomenon where bubbles in a liquid bombarded by sound waves collapse and emit a flash of light. The temperatures and pressures inside these collapsing bubbles are extreme, reaching thousands of degrees. For a time, it was speculated that this process might be focusing vacuum energy, squeezing energy from the quantum foam into a single point. It was a beautiful and compelling idea. Yet further, more rigorous investigation has pointed toward more conventional, albeit still poorly understood explanations involving plasma physics and shockwaves. The ZPE hypothesis, while not entirely ruled out as a minor contributor, is no longer seen as the primary driver. In science, the most extraordinary claim is often the least likely explanation. Before we can claim to have overthrown 200 years of physics, we must first exhaust every single mundane possibility, and the list of mundane possibilities is very, very long. This brings us to the position of mainstream science, which is often portrayed by ZPE proponents as a dogmatic suppressive conspiracy. The reality is far less conspiratorial and far more profound. The scientific community is not skeptical because it lacks imagination. It is skeptical because the principles that would have to be violated to allow for easy ZPE extraction are the very principles that make our technological world possible. They are the bedrock upon which all of physics and engineering are built. At the heart of this skepticism is a concept as fundamental as any in physics, the conservation of energy. It states that energy cannot be created or destroyed, only changed from one form to another. It is the single most important accounting rule in the cosmos. A ZPE generator would not just be changing energy, it would be conjuring new, useful energy from a baseline state, effectively creating it from nothing. It would be a fundamental violation of this sacred law, and in the entire history of science, not one single experiment has ever conclusively demonstrated a violation of energy conservation. Furthermore, the very structure of space-time, as described by Einstein's theory of relativity, seems to conspire against the idea. One of the core tenets of relativity is that the laws of physics are the same for all observers in uniform motion. This is called Lorentz invariance. The vacuum by definition must look and behave identically to everyone, whether you are standing still or flying past in a rocket at near the speed of light. But imagine you had a ZPE extractor. As your spaceship moved through the vacuum, your device would be extracting energy from it, creating a kind of drag, a resistance. This aether wind would mean that your motion relative to the vacuum is now a detectable privileged state. The vacuum would no longer be the same for all observers. You would have discovered a universal absolute frame of reference, a cosmic anchor against which all motion could be measured. This would not just be a small tweak to our understanding. It would shatter the entire foundation of relativity, a theory that has been confirmed with breathtaking precision for over a century. The vacuum's energy appears to be protected by the most fundamental symmetries of space-time itself. It is the price of a consistent reality. So the skepticism is not born of stubbornness, it is born of a deep and profound respect for the coherence and consistency of the universe. To accept the claims of a working ZPE device is to accept that the principles underlying everything from GPS, satellites and nuclear power to the expansion of the universe and the chemistry of stars are somehow deeply wrong. It's not impossible. Science is always open to revolution, but the burden of proof is and must be astronomically high. You are not just presenting a new gadget, you are claiming to have discovered a fundamental flaw in the logical architecture of existence. You are asserting that the cosmic accountant has been miscalculating for 13.8 billion years, and so we find ourselves caught in a magnificent bind. We stand before a vault containing more wealth than we can possibly imagine, a treasure that could solve our deepest problems and launch our civilization into a future of unimaginable prosperity. We can hear the treasure humming through the walls. We have even found a keyhole, the Casimir effect, that proves the vault is real. But every key we try to make, every attempt to force the lock fails. The vault appears to be sealed by the very laws that govern the act of opening it. The downward path leads us here to this impasse, where the greatest source of energy in the cosmos is guarded by the most fundamental principles of the cosmos. The dream of a utopian future powered by the void confronts the ironclad logic of thermodynamics and relativity. Is this then the end of the story? A cosmic taunt? A promise with an eternally unreadable footnote? Is the energy of the vacuum destined to remain forever beyond our grasp, a silent, untouchable backdrop to the unfolding drama of the universe? Or is there another path? Not a brute force assault on the laws of nature, but a more subtle negotiation. Perhaps our understanding of the vacuum, or even of thermodynamics itself, is incomplete. Perhaps hidden in the labyrinth of quantum gravity or the exotic physics of string theory there lies a loophole, a clever way to ask the universe for its energy not by force, but by persuasion. The direct path has led us to a wall. Now we must begin the search for a secret door, and so the great cosmic engine falls silent. The dream of cities lit by the boundless energy of the void of starships drinking directly from the fabric of space-time seems to recede, dissolving like a mirage in the face of hard, unyielding cosmic truths. For decades we chased a ghost, a titan of infinite power, only to find ourselves humbled by the sheer scale of reality, reminded that the universe does not yield its greatest secrets to brute force or wishful thinking. The roar we thought we heard in the silence of space was perhaps only the echo of our own ambition. But this is not an ending. It is a transformation. It is the quiet, deliberate moment where the alchemist, having failed to turn lead into gold, instead discovers the fundamental principles of chemistry. The pursuit of zero-point energy was never truly a failure. It was the necessary, turbulent, and often misguided childhood of a science now entering its maturity. We were like children shouting into a vast canyon, listening for a thunderous reply, when all along the true marvel was in the subtle acoustics of the canyon walls themselves, in the way our own voices were shaped and returned to us. The frontier did not vanish. It simply shrank. It collapsed from the scale of galaxies to the scale of molecules, from a question of power to a question of control. And here in the microscopic realm, the quantum vacuum is not a silent, passive reservoir of unimaginable energy. It is an active, seething, and profoundly influential environment. This is where the real work begins. We had to learn to listen to the whispers of the void rather than demand it roar. Our first coherent conversations are happening in laboratories dedicated to the impossibly small in the world of micro-electromechanical systems, or MEMS. These are machines built on the scale of a human hair, intricate silicon landscapes of gears, levers, and sensors that form the secret heart of our modern technology. They are in your phone, your car, the guidance systems of aircraft and satellites. And at this Lilliputian scale, the universe plays by different rules. Here, the Casimir effect, that gentle quantum embrace we witnessed between two plates in the void, is no longer a subtle curiosity. It becomes a tyrant. The attractive force born from the roiling sea of virtual particles creates a phenomenon known as stiction. Microscopic machine parts designed to move freely instead get stuck together, clamped by the invisible hands of empty space. The vacuum, far from being empty, actively interferes, causing our tiniest and most sophisticated creations to fail. For years, this was a problem to be overcome, an obstacle to be engineered around. But a brilliant shift in perspective has changed everything. What if we could do more than just fight this force? What if we could tame it? What if we could reverse it? This is the dawn of Casimir engineering. Researchers are now designing incredibly complex nanostructures, metamaterials, with geometries so precise they act as shapers of the void itself. Instead of simple parallel plates, imagine microscopic landscapes of interlocking combs, pillars, and trenches. By carefully arranging these shapes, scientists can manipulate the spectrum of virtual particles allowed to exist between them. They are in a very real sense tuning the nothingness. And with the right geometry, the impossible happens. The force flips. Attraction becomes repulsion. The quantum vacuum, which once clamped these tiny gears together, is now instructed to push them apart. It becomes the ultimate lubricant, a frictionless bearing sculpted from the very fabric of reality. Imagine a microscopic switch, a component in a future computer that never physically touches. It floats levitated by a pocket of engineered vacuum, able to operate millions of times a second without wear, without friction, without ever succumbing to the quantum stickiness that plagues current designs. This is not a fantasy of limitless energy. It is something far more subtle and perhaps more profound. It is the first step towards a true collaboration with the cosmos, learning the language of the quantum foam, not to command it, but to gently guide it. We are not drilling for oil in the vacuum. We are learning the art of quantum origami, folding the fabric of empty space to create new functions, to build machines that are not just times in times the universe, but are built times with times the universe at its most fundamental level. This is the new frontier, a domain where the energy of the void is not a source of power, but a tool for exquisite, unprecedented mechanical control. The dream of a cosmic engine has been replaced by the reality of a quantum gear. And from this mastery over quantum forces, an even more audacious idea begins to take shape. If we can sculpt the vacuum to push and pull on our machines, could we also use it to influence the very nature of matter? Every atom that constitutes our world, the chair you sit on, the air you breathe, the stuff of your own body, is in a constant frantic dance with the quantum vacuum. Electrons in their orbits are not following simple placid paths. They are continuously jittering, nudged and jostled by the ceaseless emergence and disappearance of virtual particles. This quantum jitter, this subtle tremor from the zero-point field, is not a minor effect. It is woven into the very definition of matter. It subtly alters the energy levels of atoms, influences the strength and angle of chemical bonds, and contributes to the fundamental properties of every substance we have ever known. We have always accepted this as a constant and unchangeable backdrop to the theatre of chemistry and physics. But what if it isn't? What if the backdrop could be changed? This is the revolutionary concept behind designer vacuums. In laboratories pushing the very limits of materials science, researchers are exploring ways to create localized environments where the rules of the quantum vacuum are rewritten. Using layers of exotic materials like graphene or custom-built photonic crystals, they aim to create a quantum cavity, a small region of space that filters the zero-point field. Inside such a cavity, certain frequencies of virtual particles might be suppressed while others are enhanced. The vacuum inside would be different from the vacuum outside, possessing a unique energetic texture. An atom placed within this bespoke void would experience a new reality. Its electrons would jitter to a different rhythm. Its chemical properties, its very identity could be altered. The implications are staggering, bordering on science fiction. Could we create a cavity that enhances the specific vacuum fluctuations needed to catalyze a difficult chemical reaction, acting as an invisible incorporeal catalyst? This could transform the production of pharmaceuticals or the creation of new efficient fuels. Could we design a vacuum environment that subtly alters the crystalline structure of a material as it forms, coaxing it to adopt a configuration that would make it a perfect superconductor at room temperature? The economic and technological, the revolution of such a discovery would dwarf the invention of the transistor. We could be on the verge of becoming architects of matter, using the void itself as our invisible anvil and hammer. This isn't about creating energy from nothing. It is about using the inherent energy of nothingness to persuade something to become something else, something stronger, something more efficient, something new. It reframes our entire relationship with the material world. For all of human history, we have been limited to the ingredients provided to us by nature. We could mix them, heat them, purify them, but we were always bound by their intrinsic properties. This new science suggests we might one day be able to change those intrinsic properties themselves by changing the very stage upon which their atomic drama unfolds. The dream of a ZPE-powered car is fading, but the possibility of using ZPE to forge the very materials that car is made from, making it impossibly light, impossibly strong, is just beginning to gleam on the horizon. We are moving from being consumers of reality to becoming its co-authors. And as we peer deeper into this microscopic realm, our journey takes its most intimate and perhaps unsettling turn. We look away from silicon chips and exotic crystals, and we look towards life itself. For billions of years, life on Earth has evolved, unfolding its delicate and complex chemistry within the embrace of the quantum vacuum. We are, each of us, collections of molecules of atoms whose every interaction has been perpetually influenced by the seething energy of empty space. We are children of the void in a far more literal sense than we ever imagined. This raises a profound and tantalizing question. Has life, through the relentless process of natural selection, already learned to harness these subtle quantum effects? We know it has done so elsewhere. The miracle of photosynthesis, the process that powers nearly all life on this planet, relies on quantum coherence to transfer energy from a captured photon to a reaction center with near-perfect efficiency. The humble European robin may use quantum entanglement to navigate using the Earth's magnetic field. These are not fringe theories. They are the frontiers of the burgeoning field of quantum biology. So, is it truly a leap to ask, if life has also learned to feel the texture of the vacuum? Consider the intricate folding of a protein. A long chain of amino acids must contort itself into a precise three-dimensional shape to function. Misfold and disease can follow. The forces that guide this celestial origami are incredibly subtle. Could the Casimir forces between different parts of the molecule, that same quantum stickiness that plagues our micromachines, play a role in guiding it towards its correct life-giving form? Could the local vacuum environment inside a cell, crowded with molecules and structured water, be different from the vacuum outside, creating a unique quantum landscape that facilitates the chemistry of life? Some pioneering scientists believe so. They hypothesize that the very medium of life is in effect a designer vacuum sculpted by evolution over eons. If this is true, it opens the door to a revolution in medicine that we can barely comprehend. Our current medical technology is in many ways remarkably crude. We bombard the body with powerful chemicals or radiation, hoping to affect the diseased cells more than the healthy ones. It is a war of attrition. But a medicine based on a deep understanding of the bioquantum realm would be different. It would be a medicine of whispers. Imagine a diagnostic tool that doesn't look for chemical markers, but instead measures the subtle shifts in the Casimir forces around a cell membrane. A cancerous cell with its altered metabolism and structure might generate a different quantum vacuum signature long before it multiplies into a detectable tumor. We could detect the shadow of the disease before the disease itself truly exists. Or consider therapeutic nanobots not as tiny submarines that mechanically attack pathogens, but as microscopic architects of the void. They could be designed to enter a specific region of the body and generate a localized field that alters the vacuum, creating an environment that encourages damaged proteins to refold correctly, or one that inhibits the specific quantum fluctuations necessary for a virus to replicate. This is not healing with energy blasts. This is healing by subtly adjusting the fundamental parameters of reality within a single cell. It is a medicine that doesn't fight biology, but instead reminds it of the correct way to be speaking to it in the quantum language it has understood all along. We are just now learning the alphabet of that language. The journey from the grandiose dream of infinite power has led us improbably back to the fragile mystery of ourselves, finding the most profound secrets of the cosmos reflected in the quiet hum of our own biology. So here we stand at the close of one chapter and the opening of another. The lure of the cosmic dynamo, the engine that would solve all our energy needs and carry us to the stars, has proven to be just that, a lure. A necessary and beautiful dream that forced us to look so deeply into the nature of nothingness that we found something far more valuable. We found not a source of infinite power, but a new dimension of control. The energy of the void is not a treasure to be plundered, but a medium to be sculpted, a canvas to be painted. Its mastery will not be measured in gigawatts, but in the perfection of a microscopic gear, in the impossible properties of a new material, in the subtle restoration of a single living cell. We have been humbled. Our adolescent dream of cosmic dominance has given way to a more mature, more intricate, and ultimately more powerful wisdom that the greatest advancements come not from shouting orders at the universe, but from learning to listen to its most subtle harmonies. The pursuit of zero-point energy has taught us that the vacuum is not a void to be filled, but a tool to be wielded. And as we learn to use this tool with increasing precision, we are not just building new technologies. We are building a new relationship with reality itself. We are transitioning from being mere inhabitants of the cosmos to becoming its partners, its collaborators, its students. And this leaves us with a final awe-inspiring question. As we learn to engineer, to sculpt and to tune this fundamental substrate, what are we truly manipulating? If we can teach nothing, to push, to build and to heal, then what truly times is times, the nature of this nothingness that permeates all of existence. And so we arrive at the shoreline of this vast, subatomic ocean. Our journey, which began with the intoxicating dream of a limitless energy source, a Promethean fire stolen from the very vacuum of space, now deposits us onto the shores of a more complex and subtle reality. The grand promise of powering our world from the ghostly hum of nothingness The vision of cities illuminated by the void itself remains for now a phantom shimmering on the horizon of what is possible. It is a humbling destination, perhaps, for a quest that started with such audacious ambition, yet it is far from a barren one. To dismiss this pursuit as a failure is to misunderstand the very nature of exploration. It is to see only the unopened treasure chest while ignoring the profound and invaluable discoveries we have made while simply searching for the key. The story of zero-point energy is in its essence a quintessentially human one. It is a narrative woven from our oldest and most primal desires, the yearning for abundance, for freedom from scarcity, for a mastery over the fundamental forces that govern our existence. From the first controlled fire that pushed back the night, to the splitting of the atom that unleashed the power of the stars, our ascent has been a story of energy. And in the quantum vacuum we believed we had found its ultimate wellspring, an infinite reservoir, promised by the strange new laws of a subatomic world. This was not just a technological dream, it was a philosophical one. It offered a vision of a future where conflict over resources might dissolve, where the burdens of labor could be lifted, and where the full potential of our species could finally be untethered from the constraints of fuel. It was a modern myth in the making. But science is the crucible where myths are tested. What we found within that crucible was not the easily tapped fountain we had hoped for, but something far more enigmatic. The universe, it seems, guards its deepest secrets with a fierce and subtle intellect. We learned that the vacuum's energy is not a passive pool waiting to be siphoned. It is instead an intrinsic structural property of space-time itself, the very ground state of being. To extract it would be like trying to take the wetness out of water while leaving the water behind, or attempting to borrow money from a bank account that has a balance of absolute zero. The energy is there, woven into the definition of existence, but it is bound by a terrible equilibrium. It is the cost of entry for the universe itself. The Casimir effect, which we witnessed as a tangible, measurable ghost pushing two plates together in the dark, stands as the most potent physical proof of this hidden world. It is a stunning confirmation that the void is not empty. Yet it is also a profound lesson in scale and accessibility. The forces it generates, while detectable and now even useful in the delicate world of nanotechnology, are infinitesimal, a whisper from the quantum realm, not the roar of a cosmic engine. They are the fleeting ripples on the surface of that deep ocean, not the powerful world-turning tide we sought to harness. Our early pioneers, with their visions of ZPE-powered spacecraft and home generators, were not wrong about the energy's existence. Their error, an error born of optimism and breathtaking ambition, was in underestimating the sheer strength of the cosmic laws that keep this power in check. They were like sailors who, having discovered the existence of water pressure at the bottom of the sea, dreamed of running a global empire on its power, without first understanding the impossible physics of bringing that crushing force to the surface. This realization forces us to recalibrate our perspective, to shift our gaze from what we had hoped to gain to what we have undeniably learned. For in the demanding pursuit of this impossible energy, we were forced to probe the nature of reality at its most fundamental level. The quest for zero-point energy, even in its perceived failure to deliver on its primary promise, has become one of the most fruitful detours in the history of modern physics. It has served as a powerful lens, focusing our attention on the strange, effervescent nature of the quantum vacuum, compelling us to confront questions we might otherwise have ignored. It is in this intellectual fallout, this cascade of unexpected insights, that the true treasure of our journey lies. Consider the role of the vacuum in the grandest story of all the birth of our universe. The theory of cosmic inflation, our best explanation for the origin of cosmic structure, posits that the universe underwent an exponential expansion in the first fractions of a second of its existence. And what powered this primordial explosion, this event that stretched a microscopic point into a cosmos, vast beyond comprehension? It was the vacuum energy of a primordial quantum field. In that violent, nascent moment, the energy of nothing was the most powerful force in existence. It was the cosmic detonator, the breath that inflated the balloon of space-time, and in its subsequent decay, it seeded the cosmos with the matter and radiation we see today. The stars, the galaxies, you and I, we are all in a very real sense the children of a zero-point energy field that existed at the beginning of time. Our quest to power our cars with the vacuum may be stalled, but we have discovered that the vacuum once powered the creation of everything. And the story does not end there. As we turn our telescopes to the heavens, we find the ghost of vacuum energy haunting the modern cosmos. The accelerating expansion of the universe, a discovery that shook the foundations of cosmology, is attributed to a mysterious force we have named dark energy. While its precise nature remains one of the greatest unsolved puzzles in science, our leading theoretical candidate is nothing less than the residual energy of the vacuum itself, a tiny, persistent, but cosmologically significant zero-point energy woven into the fabric of space is gently but inexorably pushing the galaxies apart. It is a cosmic anti-gravity, a force that will determine the ultimate fate of our universe, whether it will expand forever into a cold and lonely darkness or end in some other more exotic fate. We went looking for a way to power our toasters and stumbled upon the driving force behind cosmic destiny. This discovery, however, unveils the most profound and humbling mystery of all, a puzzle so vast it has been called the single greatest crisis in modern physics, the cosmological constant problem. Quantum field theory, the very framework that so accurately predicts the existence of ZPE, allows us to calculate its expected energy density. When we perform this calculation, the number it produces is staggering, an energy value so colossal it would defy all earthly analogies. It is a 1 followed by 120 zeros. If the vacuum truly possessed this much energy, its gravitational influence would be overwhelming. It would have ripped the universe apart in the instant of its creation. Space-time would have curled up into an infinitesimal ball before the first atom ever had a chance to form. Nothing should exist. Yet here we are. We exist. We look out at the cosmos and measure the actual energy density of the vacuum, the value represented by dark energy. That observed value is unimaginably small, barely above zero. The discrepancy between the theoretical prediction and the astronomical observation is a factor of 10 to the power of 120. This is not a mere rounding error. It is the most spectacular failure of a physical theory in history. It is a cosmic accounting error of such monumental proportions that it is difficult to even articulate. Imagine measuring the size of a single proton and finding it to be larger than the entire observable universe. That is the scale of our confusion. It is a signpost pointing toward a fundamental gap in our understanding, a signal that our most successful theories of the very large and the very small are somehow catastrophically incomplete. There must be some unknown physical principle, some deep cosmic symmetry we have not yet glimpsed, that is cancelling out this gargantuan reservoir of power, leaving behind only the delicate whisper-thin residue that we call dark energy. And so the quest for zero-point energy has evolved. It has transformed from an engineering problem into a profound cosmological investigation. The primary question is no longer, how do we tap this energy, but rather, why is there so little of it? What is the cosmic mechanism that performs this unbelievable act of fine-tuning? Solving this riddle is the holy grail for a new generation of physicists. It may require a final unified theory of physics, a quantum theory of gravity that can bridge the gap between Einstein's relativity and the quantum world. It is a problem so fundamental that its solution will undoubtedly rewrite our understanding of space, time, and matter. The energy of the void, once seen as a potential fuel source, has become the ultimate diagnostic tool, a cosmic anomaly that reveals the deepest cracks in the foundations of our knowledge. It is a constant, humbling reminder that for all we have discovered, we are still just beginning to map the territory of existence. Where then does this leave us? The dream of a utopian energy source drawn from the ether seems to have been deferred, perhaps indefinitely. The laws of thermodynamics and quantum mechanics present formidable, perhaps insurmountable barriers. But to close the book on this story would be an act of profound arrogance. Science has a long and storied history of declaring things impossible only to be proven wrong by a future generation armed with deeper insight and more powerful tools. Perhaps we are simply thinking about the problem in the wrong way. Perhaps direct extraction is indeed a fool's errand, but manipulation might be another story entirely. Could we one day learn not to drain the vacuum's energy, but to modify its properties, to engineer the vacuum itself? Theoretical physicists, ever the pioneers of the seemingly impossible, are already exploring such radical ideas. Concepts like the Alcubierre drive a speculative warp drive that would propel a spacecraft by warping spacetime around it, rely on the manipulation of vacuum energy to create regions of negative energy density. While this remains firmly in the realm of science fiction today, it is an idea rooted in the very physics we have been exploring. It illustrates a shift in thinking from using the vacuum as a fuel tank to using it as a malleable medium, a new kind of aether that can be shaped and molded to achieve extraordinary ends. Beyond propulsion, could we tailor the vacuum to influence the properties of matter within it? The energy levels of atoms, the rate of radioactive decay, the very stability of particles, all are subtly influenced by their interaction with the quantum vacuum. If we could learn to control these zero-point fluctuations in a localized region, could we create novel materials with properties currently unimaginable? Could we catalyze chemical reactions or perhaps even influence biological processes by tuning the energetic ground floor of reality itself? These are questions for the science of the 22nd century, perhaps even the 23rd. But they are the seeds being planted today in the fertile ground of our current failure to extract free energy. The allure of the void has not diminished. It has simply become more sophisticated, more nuanced, and infinitely more profound. Ultimately, the enduring legacy of our search for zero-point energy is not a machine or a power plant, but a sharpened sense of wonder. It has led us to the edge of what we know, forcing us to stare into the abyss of our own ignorance. But it is in that abyss that the future of science resides. The pursuit has reaffirmed the central tenet of all scientific endeavor, that the universe is not only stranger than we imagine, but stranger than we can times imagine. It is a place of sublime beauty and terrifying complexity, where the emptiness of space is the most potent plenum of all, where the beginning of everything was driven by nothing, and where the greatest mystery is not why there is so much energy, but why there is in fact a universe at all. Our quest continues. Not for a simple fuel, but for a deeper truth. We continue to build experiments that probe the vacuum with ever greater precision. We continue to devise theories that attempt to bridge the chasm between the quantum and the cosmic. We do this because we are an innately curious species. We are driven by an insatiable need to understand the mechanics of our own existence, to read the pages of the cosmic rulebook. The energy of the void may never light our homes, but it has unquestionably illuminated our minds. And in that brilliant clarifying light we can see the path forward. A path that stretches on toward a horizon of questions yet unasked, and of wonders yet to be discovered, all waiting for us in the profound and vibrant emptiness of space. The engine of creation may remain beyond our grasp, but the journey toward it has already changed us and the universe forever undefined.